All righty. So this is our second to last GRE session. We are going to be looking at geometry today, and I think we'll have some time for some practice problems at the end, so be prepared for that. So let's get started. So in this test, you're going to have to remember some geometry, and there's a few rules that I think people have forgotten, and I'm going to give you a few little strategies on dealing with geometry questions that you should know. First part of geometry that you're going to run into is lines and angles, and dealing with things like conjugate, or not conjugate, but complementary and supplementary angles and all that kind of fun stuff. So when you've got some figure like this, we have to know some of the relationships. So if I'm looking from a straight line to a straight line, how many degrees is that going to be? That has to be 180. What if I'm going all the way around back to where I started from? How many degrees does that have to be? 360. And the reason why we want to know that is because if they give us one or two of those angles, we want to be able to figure out other angles in that system. So if I said that this angle was 25, what is this angle right here? $155, because we know that those would have to add up to 180. We also know the other angles though because of the rule of vertical angles or opposite angles. So the opposite angles are going to be equal to each other. So what other angles do I know? Do I know this one? That has to be 25 because it's opposite of the 25 on the other side, or it's a vertical angle. And that also means that this guy must be 155. So we have to understand our basic rules of angles around intersecting lines. Now, something they do on the GRE is they do something like this. Do I have sets of intersecting lines here? Do I have any intersecting lines in this example down at the bottom of the page? But yes, I actually do. And this is why they do this. They stop it at that line, but there's actually intersecting lines here. And what I would suggest you always do is if you've got this situation where you have parallel lines and you've only got that bisector stopping at the edge, go ahead and draw in past those ends. And now all of a sudden you've got a good characteristic set of parallel lines or of intersecting lines. And this brings all those rules into play. So what they're basically doing is they're hiding intersecting lines right in your face because they don't give you a crossing, they just give it to you touching. So one of the first things I do on any figure is I start drawing all the drawing like lines past the end points, because you'll be surprised at how often that can help you figure out what some of the angles are in something. And there's also the nature of parallel lines that has this. So if this is 25, how many other 25-degree angles do I have in this picture? I have a total of 4. So, because I could say this is 25 because they're opposite angles, and then I've got this being 25 because they're co-interior angles, and then I've got this being 25 because they're opposite angles or co-exterior. So a lot of different terminology around it. You don't have to remember the terminology. You just got to know that you've got all 4 of those if these lines are parallel. And if I have a set of lines on the GRE, are they parallel if they look parallel? That's a no. They have to tell you that they are parallel. And one of the things they do to show you that lines are parallel is they'll do this. They'll draw another line in somewhere else in the figure, and they'll put a right angle and a right angle in there. Or they might explicitly say it's parallel. But you can't assume that figures on the GRE are to scale. In fact, this is not an unusual occurrence where they might give you something like this and say this is a 25-degree angle. Well, we know that's not a 25-degree angle, it's greater than 90. But they can do that and it's perfectly okay, because in the rules for the GRE, they explicitly state geometric figures are not to scale. So you have to be wary of that. So you got to use basic rules of triangles and stuff like that. All right, so what about triangles? We have to know some rules about triangles. So we know that the sum of all angles in a triangle is 180 degrees. What special kind of triangle is this? Equilateral, which means all angles and all sides are equal, because the side length of a triangle is proportional to the angle. So what are these angles going to be? $60 degrees. Oh yeah. Okay, what kind of special triangle is this guy? It's right triangle. Specifically, this one is a isosceles right triangle. What does isosceles mean? Two sides and thus two angles are equal. So that's my isosceles triangle. And why do we have to know the names of these things? Is because they may actually call it that in the question stem. An isosceles right triangle has blah, 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 blah. What is it if all three sides are unequal? And all three angles are unequal. What is that called? Ah, good. We got a scalene triangle. Yes. No sides and no angles are equal to each other. So here's another rule that I'm betting you may not remember. So if I give you two sides of a triangle, let's say this is 5 and this is 3. What's the range that this side of the triangle can be? Like, how long are my possible answers for that side of that triangle? This is where they might make it a quant comp kind of question, because they'll ask about that side of the triangle. Yeah, this is one of those little rules that you probably learned in 10th grade, and it's been so long that you're just like, I just don't remember this. So think about if I line it all straight. There's my 3, there's my 5. What's the longest it could possibly be? 3 plus 5 is 8. And then if I line it up so that they're this way, is a 0-degree angle between them, what's the shortest it could be? Not 5, but shorter than that, 2. Because the difference is 2, the sum is 8. And that's the rule. The length of the third side of a triangle is shorter than the sum, but longer than the difference of the other two sides. Because it can't actually be 8. That would be a 100-degree angle, 180-degree angle, which would mean not a triangle, it's a line. And it can't be 0 degrees because that'd also be a line. But it can be anywhere between 2 and 8 for that other side. So this is greater than 2. Wait, that was, I don't know what I'm writing there. Let me get my eraser out. Erase that. It would be greater than 2 and less than 8. Less than the sum, greater than the difference. So kind of a random rule. How about the area of a triangle? How do I find the area of a triangle? One half the base times the height. That is correct. Now you have to be careful, because what if I give you a funky triangle like this? If this is my base, what is my height? Is the height actually contained within the triangle itself? And that's a no. The height is, well, that's just terrible drawing as well. The height is going to be to the perpendicular, is going to be the perpendicular to the base. So the height in this case is this height if I extend the base out in the leftward direction. So sometimes the height itself is not within the triangle, so you have to be mindful and watchful of that. How about, let's see, if I have a right triangle, what fancy rule applies to the triangles for the side lengths? And it only applies for right triangles. I'm in general though, like we're not talking about area anymore. How do I relate the side lengths together for a right triangle? It's some dead Greek guy's thing. Yeah, Pythagorean theorem, a squared plus b squared equals c squared, and it only works with right triangles. Remembering that C is always the hypotenuse, and the hypotenuse is always opposite of the 90-degree angle, always. So, which is the only triangle on the screen right now to which this would apply? A, B, C, the isosceles triangle, because the only one that I have is a right triangle. And there we go. So, know your triangle rules. They love them. I will say that most geometry problems will probably boil down to being either a triangle problem or a circle problem. One of the two. You're usually not dealing with quadrilaterals, because quadrilaterals are other shapes you can usually break down into some combination of triangles. So triangles will be your best friend. Speaking of which, there's just some triangles that you got to recognize. And these are that are called the so-called special triangles. You don't need to use the Pythagorean theorem. You could, but you're going to speed yourself up a lot if you don't. And you want to be able to recognize them when you see them. If you see a triangle that has sides of, say, 2 and 2, and you notice that it's a 45-45 right triangle, what's the third side? Well, automatically, because I just know my special triangles, I know it's going to be 2 root 2. Or then there's the so-called 3, 4, 5 right triangle, or the 5, 12, 13 right triangle, or my 30, 60, 90, which is an x root 3, 2x right triangle. So knowing the different special triangles and watching for them is so important to the GRE. I will say that almost every single triangle problem boils down to one of these. I can't say it's always going to be this, but they know that you have limited time, so they're going to give you something that you can sort of latch onto. So look for and be able to recognize the 4 special right triangles. There's other special right triangles, also known as Pythagorean triples. It wouldn't help you to know those. These are the ones that are used almost exclusively on the GRE. Now, you will see quadrilaterals from time to time, and you do need to know some rules about them. Just that the sum of the angles in a quadrilateral, something with 4 sides, like a square or a rectangle or rhombus, is going to be 360 degrees. There is a generalized formula for all shapes that the sum of the angles is going to be 180 times their number of sides minus 2. So what would be the number of degrees in a hexagon? What would be the number of degrees in a hexagon? Bigger than 640. No worries. 720, yes, definitely 720, because I would take 6 minus 2, that's going to be 4 times 180. 4 times 180 is 720. So for any given shape, you can always figure out how many total angles it has to have within it. So this is what we call a regular quadrilateral. And when you hear the term regular, that would also apply to an equilateral triangle. What does regular mean? All blank and all blank are equal. All sides and all angles are equal. So in this case, what is the name of a regular quadrilateral? It is a square. A regular quadrilateral is a square. What is this shape? It's related to a square. A square is one of these things, but one of these things is not a square. It is a parallelogram, that is true, and it is also a rhombus. If all sides are equal, but the angles are not equal, then we call it a rhombus. And a rhombus is a type of parallelogram, but a rhombus, or all parallelograms are not rhombi. Is that a proper way to say it? Rhombi, rhombuses. What is this shape? Which, by the way, is also a parallelogram. A square is a parallelogram as well. All the angles are equal, but the sides are different. This is straight up a rectangle, that's right. And then this is my characteristic parallelogram, where the angles are different and the sides are different. So there's some interesting equivalencies we have here. Is a square a parallelogram? Yes or no? Yes. Is a rhombus a parallelogram? Yes. Is a square is a rhombus a square? A rhombus is not a square. Is a rhombus a rectangle? Nope. Is a rectangle a parallelogram? Is a square a rectangle? Yep. So we've got some one-way definitions here. All three of these are parallelograms. A square is a rectangle. And I believe that's all the relationships, because a rhombus is not a rectangle. A square is not a rhombus. Yeah, so we got those interrelationships going on in there. And then we have the weird one. What's the unusual quadrilateral? What's that leftover quadrilateral you might have to run into? The trapezoid. We have other trapezoids. So like these are both trapezoids. One's a right trapezoid, one's a non-right trapezoid, but whatever the case is, all the sides and all the angles are going to be different than each other, potentially, in these things. So we have two different area formulas you have to remember. So if I'm finding the area of a square, rhombus, parallelogram, or rectangle, what equation do I use? Like, how do I find the area of a square? I find it funny. This is the one we're struggling with. Close, Lindsay. Length times width times height would be a three-dimensional object. That's volume. So take away the height, and there you go. Length times width, or length times height, or however you want to call it. I said length times width. And so that's how I do the area of all of these figures, except for a trapezoid. I can't do that for a trapezoid. For a trapezoid, what we have to do is take the average of the two bases and then multiply by the height. So in this case, this would be base 1 and this would be base 2, because those are the parallel sides. So with the trapezoid, you have to go with the bases. The bases are the things that are on the parallel sides. So where are my bases in the trapezoid on the right side? Where are my bases in the trapezoid here? I would use the left and the right side. B1 would be this, and B2 would be this, and my height would be this. Because I have to have two parallel sides be the bases. So the parallel sides are your bases. So trapezoids are a little weird. What I usually do with trapezoids, though, is I turn them into usually a rectangle and one or two triangles. Because again, triangles are really your home base, because all of these figures can actually be triangles in some way, shape, or form. Like if you look at the rhombus, for example, it's like a rectangle and two triangles, like here, and then you can split this into two triangles. Most figures can be split into triangles. Alrighty. How about circles? What do we know about circles? So let's see. Which line is a diameter? Which line is a diameter in this circle? AB is a diameter. Which line is the radius? OC because O is the origin. That's my radius, which is half of a diameter. What would you call PQ? It has a name. There we go. This is one of those, that's like a deep cut in geometry, right? It's a chord. It's a chord. And the chords will always be greater or less than the length of diameter. Always has to be less than the diameter. Although technically the diameter is a chord itself, but we never call the diameter a chord. Will chords be longer or shorter than the radius? They could be both. A chord could be longer than the radius. It could be shorter than the radius. We just don't know. All right. What about the area of a circle? What's the area of a circle equal to? Okay, pi r squared. On the GRE, I would encourage you guys to remember that pi is often in the answer choices, which means you don't want to go ahead and multiply by 3.14 if you're doing area or something like that, because the pi might actually be in the answer choices and you'd be doing yourself a disservice. So don't change pi into 3. And I just said 3, yes. For something like standardized test, treat pi like it's 3. You don't have to actually do 3.14. Just keep the math simple. But don't simplify pi until the last step to find out if you actually need it or not. And what is the circumference of a circle? Two pi r, that is correct. Or also pi times the diameter. So you can use either one of those, and there might be cases to use pi times the diameter versus 2 pi r. All right, now we've got some interesting shapes here that we can create with circles. We can create a quadrilateral like this inscribed within a circle. And what we have is the central angle and the arc that it intercepts. So this difference is here, we've got alpha, which is the central angle, and we got theta, which is the inscribed angle. The difference is central angle goes to the origin. These are both radii. And that's helpful to know because if I know the radius of my circle, then I know those two sides of my quadrilateral. Then I've got an inscribed circle. Does anybody remember the ratio between the central angle and the inscribed angle? Because it actually comes up more than you'd be surprised how often it comes up. There is a basic relationship between the central angle and the inscribed angle. At the very least, which one's bigger? The central angle's bigger by how much? Exactly 2 times. That's right. Nice memory. Good job. So the central angle is twice as large as the inscribed angle. So if my inscribed angle is 45 degrees, what is my central angle? $90 degrees, which means what's this angle? $270 degrees, which means what's the other two angles in my quadrilateral? $22.5. That's right. So from surprisingly little information, if they just told you he had the inscribed angle of 90 degrees, you know all the other angles in this quadrilateral, because 90 will get you the, or if you knew the inscribed angle, that's where I started. If you know the inscribed angle, it's 45, then you can find the central, which is 90, which finds the other angle, the opposite angle, as 270, which you can figure out the other two because they're parallel to each other, would be 22.5, or not parallel to each other, but equivalent to each other. So there you go. One number gives you all these other numbers, and that's what they do on the GRE, is they give you just like this one piece of info, and you just got to keep going down the rabbit hole and finding all these other angles. Then another rule that they use is this one, where these are called tangent lines, and tangent lines are tangent to the circle at that position. Let me erase this 360 here so we can see this better. So tangent lines come right up against the edge of the circle, and they're perpendicular to radii. They're perpendicular to radii. So I already know two of the angles in this thing. I know those are both 90 degrees. So can I figure this angle out? Sure, if they give me the central angle. So if my central angle is, say, 120 degrees, what's my fourth angle in this quadrilateral? It's going to be 60 degrees. So they'll give us these kind of unusual looking shapes, but again, it comes down to quadrilaterals and triangles. And then what I would probably do in this question is turn this into what special right triangle? What special right triangle am I looking at here? What's this angle? Yeah, it's a 30, 60, 90. 30, 60, 90. Which tells me if I know the radius is 5, what is my hypotenuse? Remember, x root 3, 2x. X root 3, 2x. So my hypotenuse is 2x, which means if my radius is 5, my hypotenuse is 10. And this side would be 5 times root 3. So there's just so much you can get from so little with these geometry problems. And that's, I think, is why people sometimes get intimidated with the geometry, is because they don't give you a lot of information. It seems like they're sort of hamstringing you with that, yet it's all there. Like, you just got to know your rules and how to find angles from other angles and find sides from other sides. And that's what you got to practice when it comes to the GRE.